The knapsack problem or rucksack problem is a problem in combinatorial optimization. Given a set of items, each with a weight and a value, determine the number of each item to include in a collection so that the total weight is less than or equal to a given limit and the total value is as large as possible. It derives its name from the problem faced by someone who is constrained by a fixed size knapsack and must fill it with the most valuable items. The problem often arises in resource allocation where there are financial constraints and is studied in fields such as combinatorics, computer science, complexity theory, cryptography, applied mathematics, and daily fantasy sports. The knapsack problem has been studied for more than a century, with early works dating as far back as 1897. It is not known how the name knapsack problem originated, though the problem was referred to as such in the early works of mathematician Tobias Dantzig, suggesting that the name could have existed in folklore before a mathematical problem had been fully defined. Applications. A 1998 study of the Stony Brook University algorithm repository showed that, out of 75 algorithmic problems, the knapsack problem was the 18th most popular and the 4th most needed after KD trees, suffix trees, and the bin packing problem. Knapsack problems appear in real-world decision-making processes in a wide variety of fields, such as finding the least wasteful way to cut raw materials, seating contest of investments and portfolios, seating contest of assets for asset-backed securitization, and generating keys for the Merkle-Hellman and other knapsack cryptosystems. One early application of knapsack algorithms was in the construction and scoring of tests in which the test takers have a choice as to which questions they answer. For small examples, it is a fairly simple process to provide the test takers with such a choice. For example, if an exam contains 12 questions each worth 10 points, the test taker need only answer 10 questions to achieve a maximum possible score of 100 points. However, on tests with a heterogeneous distribution of point values, i.e., different questions are worth different point values, it is more difficult to provide choices. Foeman and Weiss proposed a system in which students are given a heterogeneous test with a total of 125 possible points. The students are asked to answer all of the questions to the best of their abilities. Of the possible subsets of problems whose total point values add up to 100, a knapsack algorithm would determine which subset gives each student the highest possible score. Definition. The most common problem being solved is the 0 to 1 knapsack problem, which restricts the number xi of copies of each kind of item to 0 or 1. Given a set of n items numbered from 1 up to n, each with a weight y and a value v, along with a maximum weight capacity w, maximize subject to n. Here xi represents the number of instances of item I to include in the knapsack. Informally, the problem is to maximize the sum of the values of the items in the knapsack so that the sum of the weights is less than or equal to the knapsack's capacity. The bounded knapsack problem removes the restriction that there is only one of each item, but restricts the number of copies of each kind of item to an integer value. Maximize subject to and the unbounded knapsack problem places no upper bound on the number of copies of each kind of item and can be formulated as above, except for that the only restriction on is that it is a non-negative integer. Maximize subject to and one example of the unbounded knapsack problem is given using the figure shown at the beginning of this article and the text, if any number of each box is available, in the caption of that figure. Computational complexity. The knapsack problem is interesting from the perspective of computer science for many reasons. The decision problem form of the knapsack problem is NP-complete, thus there is no possible algorithm both correct and fast on all cases. While the decision problem is NP-complete, the optimization problem is NP-hard, its resolution is at least as difficult as the decision problem, and there is no known polynomial algorithm which can tell, given a solution, whether it is optimal. There is a pseudo-polynomial time algorithm using dynamic programming. There is a fully polynomial time approximation scheme, which uses the pseudo-polynomial time algorithm as a subroutine, described below. Many cases that arise in practice, and random instances from some distributions, can nonetheless be solved exactly. There is a link between the decision and optimization problems in that if there exists a polynomial algorithm that solves the decision problem, then one can find the maximum value for the optimization problem in polynomial time by applying this algorithm iteratively while increasing the value of k. On the other hand, if an algorithm finds the optimal value of optimization problem in polynomial time, then the decision problem can be solved in polynomial time by comparing the value of the solution output by this algorithm with the value of k. Thus, both versions of the problem are of similar difficulty. One theme in research literature is to identify what the hard instances of the knapsack problem look like, or viewed another way, to identify what properties of instances in practice might make them more amenable than their worst-case NP-complete behavior suggests. The goal in finding these hard instances is for their use in public key cryptography systems, such as the Merkle-Hellman knapsack cryptosystem. Solving. Several algorithms are available to solve knapsack problems, based on dynamic programming approach, branch and bound approach or hybridizations of both approaches. Dynamic programming in advanced algorithm unbounded knapsack problem. If all weights we wish to maximize total value subject to the constraint that total weight is less than or equal to, then for each defined to be the maximum value that can be attained with total weight less than or equal to, then is the solution to the problem. Observe that has the following properties. Where is the value of the ith kind of item? Here the maximum of the empty set is taken to be 0. Tabulating the results from up through gives the solution. Since the calculation of each involves examining items, and there are values of to calculate, the running time of the dynamic programming solution is dividing by their greatest common divisor is a way to improve the running time. The complexity does not contradict the fact that the knapsack problem is NP-complete, since, unlike, is not polynomial in the length of the input to the problem. The length of the input to the problem is proportional to the number of bits in, not to itself. 0/1 knapsack problem. A similar dynamic programming solution for the 0/1 knapsack problem also runs in pseudo-polynomial time. Assume a strictly positive integers, defined to be the maximum value that can be attained with weight less than or equal to using items up to. We can define recursively as follows. If the solution can then be found by calculating. To do this efficiently we can use a table to store previous computations. The following is pseudocode for the dynamic program. 1. Input. 2. Values. 3. Weights. 4. Number of distinct items. 5. Knapsack capacity. 6. 7 for J from 0 to W. Do 8 meters. 0 J equals 0. 9. 10 for I from 1 to N. Do 11 for J from 0 to W. Do 12 if W I 1 less than equals J, then 13 meters I J equals max 14 else 15 meters I J equals M I 1 J. This solution will therefore run in time and space. Additionally, if we use only a one-dimensional array to store the current optimal values and pass over this array times, rewriting from to every time, we get the same result for only space. Meet in the middle. Another algorithm for 0 to 1 knapsack, discovered in 1974 and sometimes called meet in the middle due to parallels to a similarly named algorithm in cryptography, is exponential in the number of different items but may be preferable to the DP algorithm when is large compared to n. In particular, if the are non-negative but not integers, we could still use the dynamic programming algorithm by scaling and rounding. But if the problem requires fractional digits of precision to arrive at the correct answer, will need to be scaled by, and the DP algorithm will require space and time. Meet in the middle algorithm input, a set of items with weights and values output. The greatest combined value of a subset partition the set 1 n into two sets A and B of approximately equal size. Compute the weights and values of all subsets of each set for each subset of A. Find the subset of B of greatest value such that the combined weight is less than W. Keep track of the greatest combined value seen so far. The algorithm takes space, and efficient implementations of step 3 result in a runtime of, as with the meet-in-the-middle attack in cryptography, this improves on the runtime of a naive brute force approach, at the cost of using exponential rather than constant space. Approximation algorithms. As for most NP-complete problems, it may be enough to find workable solutions even if they are not optimal. Preferably, however, the approximation comes with a guarantee on the difference between the value of the solution found and the value of the optimal solution. As with many useful but computationally complex algorithms, there has been substantial research on creating and analyzing algorithms that approximate a solution. The knapsack problem, though NP-hard, is one of a collection of algorithms that can still be approximated to any specified degree. This means that the problem has a polynomial time approximation scheme. To be exact, the knapsack problem has a fully polynomial time approximation scheme. Greedy approximation algorithm. George Dantzig proposed a greedy approximation algorithm to solve the unbounded knapsack problem. His version sorts the items in decreasing order of value per unit of weight. It then proceeds to insert them into the sack, starting with as many copies as possible of the first kind of item until there is no longer space in the sack for more. Provided that there is an unlimited supply of each kind of item, if is the maximum value of items that fit into the sack, then the greedy algorithm is guaranteed to achieve at least a value of. However, for the bounded problem, where the supply of each kind of item is limited, the algorithm may be far from optimal. Fully polynomial time approximation scheme. The fully polynomial time approximation scheme for the knapsack problem takes advantage of the fact that the reason the problem has no known polynomial time solutions is because the profits associated with the items are not restricted. If one rounds off some of the least significant digits of the profit values, then they will be bounded by a polynomial and 1 epsilon, where epsilon is a bound on the correctness of the solution. This restriction then means that an algorithm can find a solution in polynomial time that is correct within a factor of the optimal solution. An algorithm for FPTAS input epsilon 0, 1, a list A of n items, specified by their values, and weights output S. The FPTAS solution P equals max, the highest item value K equals epsilon P, and for I from 1 to n do equals Kn to return the solution S. Using the values in the dynamic program outlined above theorem, the set computed by the algorithm above satisfies where is an optimal solution. Dominance relations. Solving the unbounded knapsack problem can be made easier by throwing away items which will never be needed. For a given item I, suppose we could find a set of items J such that their total weight is less than the weight of I, and the total value is greater than the value of I. Then I cannot appear in the optimal solution, because we could always improve any potential solution containing I by replacing I with the set J. Therefore, we can disregard the ith item altogether. In such cases, J is said to dominate I. Finding dominance relations allows us to significantly reduce the size of the search space. There are several different types of dominance relations, which all satisfy an inequality of the form, and for some wherein the vector denotes the number of copies of each member of J. Collective dominance. The ith item is collectively dominated by J, written as If the total weight of some combination of items in J is less than Y and their total value is greater than Y, formally, and for some, i.e., verifying this dominance is computationally hard, so it can only be used with a dynamic programming approach. In fact, this is equivalent to solving a smaller knapsack decision problem where 2V equals Y, W equals Y, and the items are restricted to J. Threshold dominance. The ith item is threshold dominated by J, written as, if some number of copies of I are dominated by J, formally, and for some in. This is a generalization of collective dominance, first introduced in and used in the EDUK algorithm. The smallest such defines the threshold of the item I, written. In this case, the optimal solution could contain at most copies of I. Multiple dominance. The ith item is multiply dominated by a single item J, written as, if I is dominated by some number of copies of J, formally, and for some i.e. This dominance could be efficiently used during pre-processing because it can be detected relatively easily. Modular dominance. Let B be the best item, i.e., for all I. This is the item with the greatest density of value. The ith item is modularly dominated by a single item J, written as, if I is dominated by J plus several copies of B, formally, and i.e. variations. There are many variations of the knapsack problem that have arisen from the vast number of applications of the basic problem. The main variations occur by changing the number of some problem parameter such as the number of items, number of objectives, or even the number of knapsacks. Multi-objective knapsack problem. This variation changes the goal of the individual filling the knapsack. Instead of one objective, such as maximizing the monetary profit, the objective could have several dimensions. For example, there could be environmental or social concerns as well as economic goals. Problems frequently addressed include portfolio and transportation logistics optimizations. As a concrete example, suppose you run a cruise ship. You have to decide how many famous comedians to hire. This boat can handle no more than 1 ton of passengers and the entertainers must weigh less than 1,000 pounds. Each comedian has a weight, brings in business based on their popularity and asks for a specific salary. In this example you have multiple objectives. You want, of course, to maximize the popularity of your entertainers while minimizing their salaries. Also, you want to have as many entertainers as possible. Multi-dimensional knapsack problem. In this variation, the weight of knapsack item is given by a d-dimensional vector and the knapsack has a d-dimensional capacity vector. The target is to maximize the sum of the values of the items in the knapsack so that the sum of weights in each dimension does not exceed. Multi-dimensional knapsack is computationally harder than knapsack, even for, the problem does not have EPTAS unless PNP. However, the algorithm in is shown to solve sparse instances efficiently. An instance of multi-dimensional knapsack is sparse if there is a set for such that for every knapsack item, such that an such instances occur, for example, when scheduling packets in a wireless network with relay nodes. The algorithm from also solves sparse instances of the multiple-choice variant, multiple-choice multi-dimensional knapsack. Multiple knapsack problem. This variation is similar to the bin packing problem. It differs from the bin packing problem in that a subset of items can be selected, whereas, in the bin packing problem, all items have to be packed to certain bins. The concept is that there are multiple knapsacks. This may seem like a trivial change, but it is not equivalent to adding to the capacity of the initial knapsack. This variation is used in many loading and scheduling problems in operations research and has a PTAS quadratic knapsack problem as described by Wu et al. The quadratic knapsack problem maximizes a quadratic objective function subject to a binary and linear capacity constraint. The quadratic knapsack problem was discussed under that title by Gallo, Hammer, and Simon in 1980. However, Gallo and Simon attribute the first treatment of the problem to Witzkel in 1975. Subset sum problem. The subset sum problem is a special case of the decision and 0 to 1 problems where each kind of item, the weight equals the value. In the field of cryptography, the term knapsack problem is often used to refer specifically to the subset sum problem and is commonly known as one of CUP's 21 NP-complete problems. The generalization of subset sum problem is called multiple subset sum problem, in which multiple bins exist with the same capacity. It has been shown that the generalization does not have an FPTAS software. Popular culture. Neil Stephenson provides an example of the knapsack problem in Chapter 70 of his novel Cryptonomicon, to distribute family heirlooms. The knapsack problem occurs commonly in role-playing games, both digital and paper-based, where the player character is constrained by their encumbrance threshold when carrying items and treasure, which regularly forces the player to evaluate the items' value-to-weight ratio in order to bring only the most valuable items to a merchant.